Hey guys, so today I'm going to talk to you a little bit about your section 4.6, which is on counting techniques. So how I plan on doing that as your learning goal is first just tying in what we did in the previous sections with using tree diagrams. And then our new piece is being able to learn and apply counting techniques, including factorials and using special buttons that are used in our calculators to help figure out the different combinations that there are given a situation. Okay, so you will need your calculator for this particular lesson if you want to have it side by side as you watch your video here on YouTube. It would be a great idea. Okay, so we're looking for our scientific calculator, and in that scientific calculator, the particular button that I want you to focus on is the factorial button. So it looks like an exclamation mark. Okay, for my Casio, I have the FX300 ES Plus, and it looks like an X, and there's an exclamation mark, and you will probably find it in your secondary function, so looking at your shift button or second button, depending on what version of a calculator that you have. Unfortunately, because I'm not obviously there with you guys, if you are not sure where your factorial button is located on your calculator, you can always just go on YouTube or even just do a Google search and try and figure out where your factorial button is, but you're basically just looking for an exclamation mark. Okay? So I'll go ahead and get started. We're going to talk today a little bit about combinatorics, which is a branch of mathematics which deals with organized counting. Okay, so for organized counting, it could be interpreted in so many ways, and I thought maybe we could just start with the most simplest and basic understanding of thinking, how can we line up children to play in a game? Okay, so our situation here is you're trying to put three children represented by A, B, and C in a line for a game. Okay, so very similar to maybe a recess game or even a gym game you might recall playing when you were very young. You can take a look at my stick figures that I have produced here. So we'll say child A, child B, and child C need to form a line. So in the arrangement that they're currently in, A, B, C is definitely an option. Similarly, I could switch it up and do BCA, I could do CBA, and I could do a couple more, right? So the best way to help figure this out, to ensure that we don't miss any as we're doing a count for them, is using a visual. So we can use a tree diagram. We want to figure out how many different orders are possible. Okay, so for your line, I can start with child A, I can start with child B, or I can start with child C. So any of those students or children have the ability to start the line. If I do go with child A as a second position, I can have child B follow or child C. Okay, I could do the same thing out of B. It could be child A, or it could be child C for the second spot. And if I go to my third line, if I started with child C, that would either give child A or child B the second spot. Okay? Now obviously we have one more spot that we need to consider for each of our branches, so that would be A, B, C, which is similar to my first arrangement that I have there that I just circled to the right. Okay, if I do AC, my last student would be B. I could do BAC, I could do BCA, I could do CAB, or I could do CBA, so if I were going backwards. So if we were to count in total all of our arrangements, well, we would say, well, there's 1, 2, 3, 4, 5, 6 different ways to arrange these 3 students or children for a game. Okay, so there's 6 different order possibilities. Okay, now we can also use our multiplication rule. for counting, so meaning find the product of the possible outcomes in each step of the sequence. Okay, so in terms of looking at those positions, so if I had my first spot, my second spot, and my third spot, my choice for the student who starts the line, I do start with 3 choices, meaning I could have child A, child B, or child C start. Okay, now for my second choice, because one already started the line, I then have 2 children that I can choose from. Okay, so you can even see in our tree diagram, there's 2 choices for each branch extension from the first round. Okay, and then for our third choice, I then have one last child that I can add to that line because the other 2 have already picked. Okay, so to find the product of the possible outcomes, our rule is just to multiply them, right? Multiply along the branches, so it's 3 times 2 times 1, which is 6. So you'll notice it is the same outcome with what we did in part A, where we did a tree diagram to actually visualize. Okay, but this exact process is what it means to figure out what are different combinations in ways of which you might need to organize numbers, right? So today we're just focusing on how to organize numbers given the situation that they're in. So we have our fundamental principle of counting, the FPC. So it reads, if you choose from m items of one type and n items of another, then together they can be chosen in m times n ways. Exactly what we did in the arrangement of children. Okay, so in this way we would multiply m times n. If we had 3 possibilities, notice you could do m times n times p. And in that equation, you'll notice m represents a number of ways the first event stage can occur, so that first position in arranging the children for the game. N represents a number of ways the second event or stage can occur, and then p represented the number of ways the third event or stage can occur. Okay, so that's going to be how we're going to start the principles for our conversation today on combinatorics. Okay. So let's consider this. We have to figure out how many 4-digit numbers are there. Okay, so if we were to think about the possible numbers, we would say, well, there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I just listed 10 different numbers, all ranging from 0 to 9. Now, to start our number, because it's a 4-digit number, the numbers in our first spot is very important because it can't be 0 in that case, right? My options are going to be either 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay? So that means there's 9 possibilities. For my second digit, I can actually include numbers 0 to 9. Okay, the reason why I couldn't contain it or include it in my first spot is because if I put 0 in the first spot, then that wouldn't be a 4-digit number, that would be a 3-digit number, right? Because we read 412 as a 3-digit number, regardless if it's written as 0412. Okay? Okay, so in this case, we actually have 10 possibilities. For our third spot or position, we have the same outcome. We can have 10 possibilities. And the same outcome for our fourth spot, where we have 10 possibilities. Okay, so what we can do here is we can multiply 9 times 10 times 10 times 10, and that represents 9,000 different combinations. Okay, that's how many 4-digit numbers there could be. Make sense? Okay, so move on then to a few different scenarios. So we're going to consider codes with and without repetition. Okay, so in this situation here, we have a code consists of 3 letters followed by 2 numbers. Okay, repetition is allowed. How many different codes are available? So this actually piggybacks off of our last example where we were dealing with possible digit numbers. So in our first 3 spots, we know that they have to be letters. Okay, in our alphabet, we know that there are 26 letters in the alphabet, so that leaves us as 26, 26, and 26. Okay, repetitions are allowed, so meaning each time we can have repeating letters, so it's not like it's one less in our options available. Okay, in our digits, as we did earlier, we noticed there are 10 possible outcomes. Okay, and using our multiplication rule, we can just multiply 26 times 26 times 26 times 10 times 10. Okay, and that will leave us with 1,757,600 different codes that are available. Okay, now how would your answer change if repetition is not allowed? Well, that's simple, right? So again, our first 3 were letters. At first choice, we have 26 letters. Now that we've used that 1 letter, we now have 25 letters, and then 24 letters. And the same thing applies with our digits. So at first choice, we have 10 digits, and when one is used, it is then 9 digits. Okay? So in that scenario, we then would have 1,404,000. Okay, so now we get into different conditions. So for number 3, this one's an interesting setup. So how many 5-digit even numbers are there if repetition is allowed? Okay, so again, we're setting up 5 different slots. 3, 4, 5. Okay, even numbers. Even numbers would be like 2, 4, 6, 8, 10. Or, sorry, 0, 2, 4, 6, 8. 10 is a 2-digit number. Okay, so 0, 2, 4, 6, and 8 would be our options. Okay, and for it to be an even number, the most important thing that we need to consider is actually the last digit as a starting point. Okay, so for it to be an even number like 10, 20, 15, 48, 222, the last digit is either 0, 2, 4, 6, or 8. Okay, so to be even, it has to end in 1, 2, 3, 4, any 5 of those options. Okay, the numbers in the second, third, and fourth slot don't matter, right? We're not limited in that way. So they can be anywhere from 0 to 9. Okay, and then we can go to our first slot. So because the first digit can't be 0, like we discussed in our example number 1, we actually have 9 options for our first value for it to actually be a 5-digit number. Okay, so we could just multiply those values there. We got 9 times 10 times 10 times 10 times 5, and that would give you your final solution. 45,000. Okay. All right. So we can consider some club examples as well. Okay, so considering what happens without repetition. So a math club has 8 members. In how many ways can a president, vice president, and secretary be chosen? Okay, so for your presidential role, we have 8 possibilities. For your vice president role, if one is president, that means you have 7 possibilities. And last but not least, for your secretary, that will leave you within 6 possibilities for that role, meaning that there can be 336 ways that those positions can be chosen. Okay? Okay. And then in this one, so in how many ways can 4 boys, so again highlight as you go through the information, and 3 girls be seated along one side of a table if Johnny and Caitlin must sit on opposite ends? So we got 1, 2, 3, 4, 5, 6, 7. Okay, so that means our first spot and our last spot are going to be very important. That's either going to be J or C. Okay, so we have 2 options in our first position, and then if J is chosen, then that means C is going to be, or Caitlin is going to be at the very end. Similarly, if Caitlin is chosen for the start of the front of the line, then that means Johnny will be at the end. So at the end, Johnny and Caitlin, that's basically where their positions will be. Okay, now we're going to consider the people in between. Okay, so I just took away 2 spots. Okay, so the first spot and the last spot. So now, if we had 7 spots, we've taken up 2, we have 5 left. And then by the third spot, we have 4 left, times 3, times 2, times 1. Okay, and then we just multiply, and we get 540 ways to be seated. Okay, so you can see with I always mess up this word, combinatronics, there we go, there are multiple ways that we can deal with numbers, whether it means that we're seating people, finding different positions for a presidential team, looking at codes, right? So dealing with digits, whether it's with letters or with numbers, you can see that there are different ways that we can figure out how many organized counting opportunities there may be given a situation. Okay, so we're going to move along, and we're going to consider the additive principle of counting, or the sum rule. Okay, so what this reads is, if you choose from either m items of one type or n items of another, then together they can be chosen in m plus n ways. Okay, so again, this depends on the reading of the question, right? So we can take a look at how a question could be set up to I guess work through in that manner. So sailing ships would send messages with signal flags flown from their masts. How many different signals are possible with a set of 4 distinct flags if a minimum of 2 flags are used for each signal? Okay, so some things to highlight. The set of 4 distinct flags if a minimum of 2 flags are used for each signal. Okay, so let's just consider how many flags are possible. We could have 2 flags here, 3 flags, 4 flags. Okay, now if a minimum of 2 flags are used for each signal, if 2 flags are given, that would be 4 times 3, which would be 12. Okay, if we use 3 flags, that would be 4 times 3 times 2, which would be 24. And then if we're considering just 4 flags, 4 times 3 times 2 times 1, which is 24. So with this additive principle of counting, we're basically going to take the signals used for each of the flags going from 2 to 3 to 4, and then we're just going to add them up. Okay, so for your total, it should be 12 plus 24 plus 24, which is 60 possible ways. Okay, all right. So now I'm going to get into this idea of factorials. Okay, so factorials are actually super, super fun. There's a couple of guidelines, and again, now would be a good time to get your calculator ready to see if you can find that factorial button. Again, on my calculator, it is an X with the factorial button, which represents something that looks like an exclamation mark. So many counting and probability calculations involve the product of a series of consecutive integers. Factorial notation can be used to write such expressions. The symbol for this notation is n factorial. Okay, so even if we could just go back up to our example here, if I could just highlight this, 4 times 3 times 2 times 1, I wanted a different color, let's try that again, 4 times 3 times 2 times 1, okay? That would be like writing 4 factorial, because 4 factorial takes all of the numbers, writes them in descending order, and multiplies all those numbers till you get to 1. Okay, so it's 4 times 3 times 2 times 1. Similarly, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so you can even try it on your calculator once you find that button. But n factorial for any natural number, assuming they have to obviously be positive numbers or include 0, n factorial is equal to n times n minus 1 times n minus 2 and so forth. Okay, so like we showed you with the 4 factorial, 4 minus 1 is 3, 4 minus 2 is 2, 4 minus 1 is 1, or 4 minus 3 is 1. Okay. So a couple of things to consider. Okay, so 0 factorial does equal 1, n factorial over n factorial do cancel out to create 1. And your third rule is when you have n factorial over 0 factorial, your answer is actually just equal to n factorial. Okay, and we actually will be able to see these in action in the examples I'm about to do with you. Okay, so we're going to evaluate or simplify. Okay, so remember 7 factorial again is like doing 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, please try to find that factorial button for you, but you should get, when you plug it into your calculator, is 5040. Okay, even in the case of subtraction, you could take 9 factorial, type that into your calculator, you should get 362,888 for 9 factorial. Okay, and then we're going to subtract 5 factorial, where you should get 120. And then, as you know, when you subtract values, it's the same type of subtraction you do. You just actually type in those two numbers and subtract them, and you should get 362,750. Okay. For number 3, we got 9 factorial over 5 factorial. So if we were just to rewrite this, we would have 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, that is represented by 9 factorial. If we did 5 factorial, it would be 5 times 4 times 3 times 2 times 1. So you'll notice there is some overlap, right? 5 over 5 cancels out, 4 over 4, 3 over 3, 2 over 2, 1 over 1. So what I'm actually just left with is what's left in the numerator. So 9 times 8 times 7 times 6. Okay? So that actually just comes out to 3,024. Hopefully we're doing okay so far with all of this. They actually get fun the more that you practice. Hopefully you get to see that joy as well. Alrighty. Okay, so if we have then a product that's in the denominator. So looking at our denominator, we have 7 factorial times 3 factorial. So again, in the numerator, 10 times 9 times 8 times 7. I'm just going to skip a couple in between because I do need some extra room, but I don't have it. Okay, and then in the denominator we have 7 times 6 times 5 times 4 times 3 times 2 times 1. That's represented by 7 factorial. Okay, and then let's write out in brackets 3 factorial. So 3 times 2 times 1. Okay, so again, look as to where you can cancel. Okay, so as to where you can cancel, definitely the 7 times 6 times 5 times 4 all the way from the denominator and then obviously to the numerator that can cancel out. I have 10 times 9 times 8 that's left. I'll just move that down. And in the denominator, I should have 3 times 2 times 1. Okay, you can further simplify here if you like. So I know 9 over 3 is 3. I know 8 over 2 is 4. So what I really have left is 10 times, I'll use the colors that I had, 3 times 4. Okay, over a denominator of 1, which is like any whole number. And yeah, in total we should get 120. Okay. For one like number 5, I'm actually going to do this one like a proof. Okay, so just to simplify, to see what we actually get once we work this out, we have n plus 1 multiplied by n minus 1 factorial. Okay, so to actually proceed through this example, I'll just section it off a bit. I'm going to rewrite what I have. So I have n plus 1 multiplied by n, and then n minus 1 factorial. Okay, so with that, let's let n represent 5 per se. Okay, so what I have in my next step would be 5 plus 1, 5 minus 1 factorial. So if I simplify that, I should have 6 times 5 times 4 factorial. Okay, so 4 factorial is actually just 4 times 3 times 2 times 1. Right? That's all part of the same step. If I include that then with the 6 times 5 that I have from the previous step, I actually just have 6 factorial. And 6 factorial is basically just n plus 1 factorial. Because, remember, I had my let statement, let n equals 5. Okay, so my final answer as a simplified form would be n plus 1 factorial. That's how I would simplify that one. You could have chosen any number to represent n, and you would still come up with the same outcome. Obviously, the bigger the numbers, the longer the solution set. So if you're satisfied with this, this works just fine. Okay? Alright, we'll try, I think we have last 2 to go. You'll like the number 7, it has a little bit of factoring. Okay, so for number 6, we got n factorial over n minus 2 factorial. So for this one, let's let n equal 7. Okay, for the sake of our solution. So I would have 7 factorial over 7 minus 2 factorial. Okay, so as we know, that would just be 7 factorial over 5 factorial. So I can do this as 7 times 6 times 5 times 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1. Okay, and then when I simplify, I actually just get 7 times 6. Okay, now this is basically n multiplied by n minus 1. Okay, so how this simplifies to this. Okay, because if I sub in n, and I let be represented by 7, and then 7 minus 1 is times 6. Okay, now because your instructions, as you see here, were to evaluate or simplify, I did use a let statement to help prove it. You need to sub it back in at the very end to actually make this hold true. Okay. All right, let's go to our last one. So our last one, what we have here is n plus 1 factorial, okay, over n minus 1 factorial is equal to 20. Okay, so first what I want to just start with is interpret n plus 1 factorial. Okay, so n plus 1 factorial, just by looking at that statement, this basically takes what's in front of the factorial, which is n plus 1. Okay, then, as you know, each number descends. So n plus 1, if we were to subtract 1, that would leave us with n plus 1 minus 1, which would just be n. Okay, and then if we were to subtract 1 again, that would be n minus 1. That is what a factorial does. Okay, so similar to when we did 4 factorial, 4 times 3 times 2 times 1. They descend in numbers. Okay, so what I'm actually going to do is I'm going to take what I did there in that work, and I'm going to use it for number 7. And I'll color code it so you guys know that it's related. N minus 1. Okay. Okay. So, with what I have there, these can actually cancel. Okay, because we said n minus 1 over n minus 1, we know that cancels. I am technically just left with then 1 factorial in the denominator, and 1 factorial in the denominator is just 1. Okay. And then what I'm left with, I'm going to reset the equal sign there. We have n plus 1 times n is equal to 20. Okay, so what I can do here is apply distributive property. I should have n squared plus n is equal to 20. I'm going to bring over that positive 20 to the left side. And I'm actually going to factor. So I have to think, what are two numbers that multiply to negative 20 and add to positive 1? So two numbers that satisfy that is n plus 5, n minus 4 is equal to 0. Okay, so basically I just found my factors. I put it into factored form. Now to find your solutions, I'll just rewrite it up here. N plus 5, n minus 4 is equal to 0. Right, your solutions are then negative 5 and positive 4. But if you recall, in the not instructions, but in the I guess presentation of what factorials are. Factorials have to be a natural number, so that's any number that is 0 and positive. Any numbers that are in the positive. So actually, our n minus 5 does not count. Okay, so we can say here that n is actually just equal to 4. Okay, now this one's a little bit different. I know in the previous ones we would just simplify and use let statements to help simplify it, but in this one we could actually find a solution, and this one, our solution is 4. That will be the hardest it gets, by the way. Okay, so don't panic if that looked a little overwhelming, but hopefully you enjoy. Alright, so that takes us through what organized counting is. Okay, so looking at counting techniques and factorials. What I plan to do over the rest of this week is to finish up permutations and combinations, and then doing a little bit of probability distribution next week. Okay, so for your homework questions, please try numbers 1 to 5 here that are attached. Your solutions are at the bottom there, but please give it a shot. Definitely worth practicing.